Climate change is one of the greatest challenges of our time. The main culprit, carbon dioxide, a greenhouse gas released whenever we burn coal, oil, or gas. Based on the data in 2015, CO2 contributes to 76% of green gas emissions in the world. Before we go deep dive, let's have a look at the increasing global green gas emissions. Looking at this chart from our world in data, we can understand that emissions have continued to grow across various sectors such as energy, transport, manufacturing, agriculture, etc., driving global warming, extreme weather, and melting glaciers. We can see that there is a lot of innovations happening in the renewable energy sector. However, the implementation and the transition isn't happening quick enough. Meanwhile, global energy demand is increasing drastically due to population growth and expanding technology. So the question arises, how do we reduce emissions from industries that can't switch to green energy immediately? That's where carbon capture and storage, or CCS, comes in. It's not a silver bullet, but it's a bridge solution that can help us buy time while transitioning to cleaner energy. Some industries are particularly hard to decarbonize, like cement, chemical production, and even aviation. These sectors produce a lot of CO2, and cutting emissions there is not easy. Even with solar, wind, nuclear energy scaling up, we will still have millions of tons of CO2 being released each year. CCS can help capture these emissions at source, preventing them from entering the atmosphere while cleaner energies catch up. The first step is capture. CO2 is collected from large emission sources like power plants or factories before it escapes into the air. There are three main methods that we normally see in the industry currently. The first one is post-combustion capture, wherein the fuel is burned as usual, then use chemical scrubbing to remove CO2 from exhaust gases. The second is pre-combustion capture. Here the fuel is converted into a hydrogen-rich gas, removing CO2 before combustion. Third is oxy-fuel combustion, burning the fuel in pure oxygen instead of air, creating a gas that's mostly CO2 and water vapor, which is easy to separate. Once captured, CO2 is compressed into a supercritical liquid. It is then transported to storage sites, usually via pipelines, but sometimes by ship or truck for smaller projects. This is similar to how oil and natural gas are transported safely today. The final step is storage. CO2 is injected in deep underground reservoirs or rock formations, often more than a kilometer below the surface. We use depleted oil and gas reservoirs or deep saline aquifers. The gas gets trapped into rock pores and even over time can mineralize into solid rock. With careful site selection, monitoring, and advanced safety measures, it can stay locked away for thousands and even millions of years. CCS is not just a theory, it's already in action around the world. The Sleipner project in Norway has stored CO2 under the North Sea since 1996. The Gordon project in Australia is designed to capture up to 4 million tons of CO2 per year in deep reservoir. Petronova project in the United States captures CO2 from coal power plant using a post-combustion capture system and uses it to enhance oil recovery. Other examples include the Boundary Dam project in Canada and several pilot studies in Europe and Asia. As per the data from 2021, there are around 100 projects including existing and planned facilities around the globe. I will add a link to the data wherein you can refer to individual projects, wherein you can get an insight of the project details, including location, status, and CO2 capture capacity. So, what's the catch? Capturing CO2 requires energy, sometimes called the energy penalty, which makes CCS expensive. Storage requires strict monitoring to prevent leaks. The public trust can be an issue, as people worry about long-term safety and integrity of the system. But CCS also presents opportunities. When paired with bioenergy, it can remove CO2 from the atmosphere. It can help produce hydrogen from fossil fuels without releasing emissions. And it can decarbonize industries that cannot fully switch to renewables yet. In short, CCS can be a critical tool to bridge the gap while the world transitions to greener energy. Global CO2 emissions are still climbing, and climate impacts are becoming more visible with heat waves, floods, and storms are on the rise. Even with rapid deployment of renewable energy, we need bridge technologies that can reduce emissions immediately. CCS is one of those tools, a way to capture emissions now while cleaner technologies scale up for the future. Carbon capture and storage isn't the magic answer to climate change, but it's a powerful tool in our toolbox. Alongside renewable energy, efficiency, and lifestyle changes, it can help us cut emissions faster. The question is, will we invest enough in it, and will we use it wisely? What do you think? Is CCS worth the cost? Share your thoughts in the comments. I would love to hear from you. This is just the beginning of our engineering journey into the world of CCS. In upcoming videos, we will deep dive into the technology, the challenges, and the future possibilities. So, stay tuned.